Okay, anyway, thank you very much. So I'd like to take this opportunity to talk about concrete and the evolution of a tall building. And, you know, and in the process, I want to talk about some important concepts. And first of all, I want to talk about the concept of a tall building. You know, it's very important to think of these things as simple, because if you take a building such as the Willis Tower, used to be called the Sears Tower, as a building, but think of it as just one giant beam coming out of the ground. Because if you think of it as thousands of beams and columns, that's just too complicated. And our brains can't do it, and nor is it necessary, because the conceptualization of a tall building as a single element coming out of the ground is very, very important. And of course, the study of cantilever structures goes way back, going back to Galileo, perhaps the first modern structural theorist, who in his dialogues of 1638 speculated about the engineering mechanics of a cantilever. I can't say he got it completely right. There was a few things, but he got the conversation started. Now, while he was dealing with the cantilever coming out of the wall, a tall building is merely cantilevers out of the ground. And in many ways, it's a very conceptually simple problem, because the load only has one load path, which is downward. And through understanding it as a beam, one can come up with very clear ideas. So when we think about a tall building as a cantilever, as a beam, you know, we think of the analogy where there's parts of the building that are there to resist the shear loads, and there's other parts that are there to resist the overturning moment, just like very much like an I-beam, where the web really resists the shear and the flanges resist the moment. Now, the second very important concept that I want to talk about in relationship to tall buildings is the wind, okay? And hopefully you can see my slide. Here I have a photograph of a cloud going past the top of the John Hancock Tower here in Chicago. And you can see it's causing a vortex, a swirl in the wind. And what happens is that when the wind goes past a building or any blunt object, either a mountain or a lamppost or a building, it will generally go about in a kind of in a manner where it goes first to one side and then the other. And every time that happens, it causes a pressure differential across the building in such a way that it gets pulled from side to side, which is very much like a child on a swing. A child can go very, very high if they kick their feet at the natural harmonics of the swing. And buildings are harmonic devices also. And so it's quite common for the wind to cause a vortex shedding, which is at the natural harmonics of the wind. And because of that, we do a lot of work in the wind tunnel. Here is we actually have our own in-house wind tunnel here in Chicago that we use for our conceptual design of early studies on the design of tall buildings. Now, now that we've talked about the main concept and also about the issues of wind as the dominant concern in a tall building, let's talk about some key structural components. You know, the things that that we need are like many structures. We need strength, we need stiffness, and we need the proper systems. And concrete does a pretty good job on all three of these. You know, the strength and the stiffness. I'll talk a good bit about that here, and then the way you arrange this into proper systems. You know, tall buildings of reinforced concrete can maybe be traced back to a little over 100 years, where we talked to this building in Cincinnati, Ohio, which had, you know, fairly modest concrete strengths. It was, of course, it was only 16 stories, around cylinder strength around C15, but over time, when we get into the more modern era, the post-World War II area, there was a lot of progress was made. The concrete strengths were up to, in the 1950s, there were in tall buildings were up into the C40 range, the cylinder strength of C40, C50. If you go a decade further, we're into strengths as high as approaching C50, 60. And as the time goes on, as you go to the 1970s, we're getting some pretty good high strength concretes. We're approaching C80 concrete, and then in the 80s, there were certain cases where there was some extremely high strength concrete, such as this project in Seattle, which had the strengths of C130. The strength were actually almost a byproduct. The goal was to achieve very high stiffness, high modulus elasticity, and so I believe on this project the team used granite aggregates. We are often as much concerned, focusing on the modulus elasticity as we are on the strength in high strength concrete. I'd have to say today a typical high rise in Chicago would be in the in the range of a little bit less than this, maybe more like a C80, C90, C100, but and a bit more. But there are occasions where we go much higher. I'm sorry, I'm going the wrong direction here. Okay, now let's speak to systems. Okay, a major breakthrough happened in the 1960s with the research of Dr. Fazlur Khan and Myron Goldsmith and others, and the development of the tubular system. Here is the world's first concrete tubular system, which was built in the mid 1960s. Where conceptually they were thought of in 3 dimensions, where the building is considered to be a tube, which is punctuated with windows, but it still acts very much like a single structural tube, like a giant beam coming out of the ground. Other ideas were developed where perhaps you have a perimeter tube and then use the elevator core system as a place to have additional stiffness. We do a lot of construction where it's mixed construction. That's probably the most common today, but where you have, at least in office buildings, it's common to have a mixture of concrete doing most of the lateral work and then steel in the floor framing. But in residential, it's virtually all concrete. Different ways of mixing concrete and steel together in various towers over the ages, such as the Bank of China. Or the Jinmao Tower in China, which was the first super tall building in China, which was the lateral system was principally concrete, even though the floor framing was steel. So that brings us to the 21st century. Let me speak a little bit about the Burj Khalifa, and it is true. It's actually interesting. The bigger the problem, the taller the building, the more you have to keep the solution simple. You have to have something that's very, very efficient. And in the process of the design, we started with a building that was about 518 meters tall, which would have made it the world's tallest building by about 10 meters. Soon we were able to realize that we could go much higher. It grew temporarily to about, during the design phase, about 728 meters. And while it was still under construction, we looked to see how much higher we could go. And eventually we were able to get the height of the building up to 828 meters. The height of the building changed during the design process by 300 meters. So going from our initial scheme to our final scheme, the change in height is approximately equal to the Shard in London or the Eiffel Tower. That's how much taller it got from our initial scheme to the final scheme. And I'll talk a bit about the initial scheme was not a very, didn't work very well. I'll talk about that in a minute. So if you look at the evolution of the tall building, it is interesting that it went up relatively quickly in the early ages. It then stabilized with small incremental changes for decades, and then the Burj Khalifa was another big step forward, where Burj Khalifa was essentially 60% taller than the previous record holder for the world's tallest building. And so, just to give you an issue of scale, I wanted to show you what it would look like in Chicago, or say in Lower Manhattan in New York, or in Canary Wharf in England, or perhaps next to the Eiffel Tower. But I'd like to make a pitch today that I think we should have. I think there should be the Burj Stockholm. I think it would look very nice with the other spires that you have there in your absolutely beautiful city. Okay, but this is, but it is actually in Dubai, and there you see what it looks like. Now the building is a multi-purpose building. Here, hopefully, you see this colored rendering of the building. At the very bottom, the green part is an Armani hotel. It is, and then the blue part is residential. The brown part and the yellow part are all residential of various flavors, if you will. And that takes us from level 19 to level 108. All of those floors were sold in 2 nights back in, I believe it was 2004. And that helped to finance the construction of the tower. Now, all the purchasers were required to put up 50% of the purchase price within 6 months, and that was very helpful. Now, the pink at the top is a bit unusual. It is a boutique offices. As you may know, Dubai is where people from all that entire region go to do business, and so those are for, so we say, rich individuals, from people in the region who want to have a boutique office in Dubai for doing their business deals, and that is that is the purpose of the pink. There's also a tremendous more and more floors up there are being converted into observation deck floors. The client makes unbelievable amount of money from the observation decks. As you could tell from the rendering, the floor plans, since the building is primarily residential, it has this Y-shaped plan, which helps give privacy, but also gives the building a very wide footprint, and which is integral with the structural system. So the architecture and the structure were developed simultaneously. One did not go before the other, but they were developed at the same time. Now, when you do something that is this tall, you got to think about issues of scale. And so, this is a very, very important thing that will allow us to realize this project. And so, once again, let's go back to Galileo, and he studied issues of scale. And so, if you have a bone that fractures by bending stress, and all the stresses in the bone is from the weight of the bone, and you make it 3 times as long, it has to be 9 times as wide if it's a cylinder. If you go through the math, actually Galileo got this one right. And so, as you go from, you cannot just make some things bigger. Sometimes you have to create something new. And this is something that was also discussed by Darcy Thompson in his very famous book on growth and form, which is it's an excellent book written, approximately 100 years ago. So, as one would expect, the bone structures of a small mammal and the bone structure of a large mammal are quite a bit different. And the same thing applies to tall buildings. You just cannot scale up certain buildings. If you took the Sears Tower, or if you took me, Bill Baker, if you made me twice as tall, I'd be twice as wide, I'd be twice as thick, and I would weigh 8 times as much. It just doesn't work. If you took the Sears Tower, if you made it twice as tall, you'd have to make it twice as wide and twice as deep, and it would just be too big. You'd be too far from the window. You'd have too much floor area. So on the Burj Khalifa, we came up with a system which allowed us to that it only scales by the square. If I make it twice as tall, I'd have twice as many levels, and I'd have to make the wings a bit longer, but I don't need to make them any wider. And that was a very critical piece of why we were able to successfully come up with this building. And so here's a chart of different building systems. I actually call them different species. So it's just, if we look at these, if we think about, if we go to a natural science museum, we ever see the different species of animals. These are different species of structural systems that are appropriate at different scales. Let me talk to you a little bit about the building. You know, it's, as you know, primarily reinforced concrete. At the very top is a steel pentacle. We wanted to use very conventional systems. I remember one time I gave a lecture, and I was one of the people in the audience, was a little bit critical about why didn't I do some more unusual structural subcomponents. And my answer was I wanted the building to actually get built. Because if you're going to come up with something, systems that contractors have never seen before, and ask them to make the world's tallest building, you're probably not going to be very successful. So what we wanted to do is we wanted to have structural systems which were very familiar to many contractors, and then put them together in perhaps a little bit unique way that they could then use. And we actually had seven companies had real credible bids for the project. In the process, what we were building is a system which we called a buttress core. We find it's very useful to describe your ideas. At the beginning of a design process, it's good to let things be very free and open. But at some point where you think you're getting very close to the idea, where you are, try to describe it in words. And if it takes a lot of words, maybe you're not there yet. But if you can describe it in concise words, such as this case, the buttress core, or the John Hancock Tower, a braced tube, or the Sears Tower, a bundle tube, it helps you understand what is important. It helps you, because these tall buildings are all about resolution of conflicts. And so the question is, who gets the right of way? And certainly, in a super tall building, the important parts of the structure should get the right of way. And so once you have that clear concept, you can explain it to the rest of your team. You can explain it to the other disciplines. You can explain it to the contractor and the owner, and it helps resolve conflicts. And what it is, one can imagine that there's a vortex. The wind is going against the building. It's forming a vortex which is pushing on one of the wings, or pushing on, I'd say, two of these wings. And what happens is that the third wing acts like a buttress to resist it. In the very center is this hexagonal concrete core that goes all around the principal elevators and stairs. And that acts like an axle, because the last thing you want is for a tall building to twist in the wind, because that's very disruptive. And so we had this concrete core, which was very good for the twist, but was too slender to go to great height. So what we did is we buttressed it with the three wings of the tower. Very much like, hopefully you see this photograph of this man with an umbrella resisting the wind. And this is a human analogy of the Burj Khalifa. His front leg is like his core, and his back leg is like the buttress, and he's resisting the wind. Now, one of the most important things in a tall building, we call it managing gravity, particularly in a concrete building. The weight of the building is a very useful thing. Gravity's very reliable. You don't have to worry about the not being properly inspected. It'll be there, okay? And so what we try to do is we try to push the wind forces outward, or the gravity forces outward, to make it stable. And this is the base of the Burj Khalifa. If you look at the reinforcement, the rebar is coming out of the raft or the mat at the bottom of the building. And someone asks you, how tall is that building? What would you say? 5 stories, 10 stories? You probably would not say 160 stories. But what it is, by managing gravity and I'll talk a bit about how we controlled the wind, we were able to reduce the forces that we have no tension at the base, even in a storm that happens once every 1,700 years. So if you have a storm, a 1,700 year return period on your windstorms, you still do not have any tension at the base of the Burj Khalifa. Now, as I said earlier, your wind is hugely important in tall buildings. And so what we did is we did a whole series of wind tunnel testings, to figure out the forces on the building. And then we essentially tuned the building like a musical instrument to get certain mode shapes and generalized mass and periods and certain behavior. And remember the analogy of and then we shaped the building. And remember the analogy of the child with 2 feet kicking in unison, going very high. Well, what we did is we figured out that the building had 3 benign directions, which is when the wind blew into one of these legs. It was like a cutwater. It was very benign. But when the wind blew between 2 of the wings, it was not very benign. It had big forces. And so what we did is the engineers and the architects working very closely together, looked at ways to reshape the building multiple times as it goes up. So what happens is that the analogy to the child on the swing, rather than have 2 feet that are kicking in unison, you essentially have 27 feet. And because the vortex shedding comes off at different rates for every cross section, instead of these 27 feet kicking in unison, they're all kicking a little bit different rate, and so the swing goes nowhere, and the dynamic forces are quite modest. And so after just 3 shapings here, hopefully you see this chart with a red line, we were able to reduce, after just a few shapings of the building, we were able to reduce the wind forces quite a bit. The red line represents a 100-year storm, which we looked at. And so in the process, we were able to come up the tower, which was much taller than where it is, where we started. Now, it turns out that the first shape that we had did not work very well. We had very large moments of acceleration. And so what we did is we went back in the wind tunnel and we reshaped the building a lot. And in the process, the forces went way down and the motions went way down. In fact, I sometimes think if the first shape had not behaved so badly, we probably would have just stopped there. But because it behaved badly, we had to do a lot of fairly important studies and reshaping of the building. And because of that, we were able to go much taller than we ever thought we did. The construction is concrete, of course. And this stuff is like magic. We should give it a new name. Look at the properties of this material. This is not the stuff that's in the sidewalks. And we were not overly ambitious in the strength. It was a C80, so it was a cube strength of C80. So it was a 64 cylinder design strength. It was kind of what you could get in Dubai at the time. You can now get better stuff. But what was delivered to the site was 100, or 80, 100, 80 cylinder, 100 cube strength. Very high modulus elasticity, very, very amazing material. The contractor figured out how they could pump the concrete 600 meters in the air, and they tested this by running pipes back and forth across the desert floor until they got the pressure loss that you would expect to see from going vertically that high. And so I'll take you through the construction sequence. It went pretty fast. The superstructure, foundations were finished in like late 2004. The project sat there for a while there's some contractual negotiation going for a while. But then in April 2005, the construction went, and the building topped out in 2009 and was opened in 2010. So the construction time was fairly reasonable. And as you can see, as it went up and up, the cladding contractor went bankrupt on us, so it took a while to get another contractor on board. So you saw the bare structure for quite a while. At the very top, we couldn't build the spire. We couldn't build the spire from outside the building because we couldn't get cranes up that high. So we built it inside the building, and then we jacked it into position using Fresnay jacks. The building got up. The spire is up there. We actually did some very sophisticated wind engineering on the spire, at the very top. Because the spire is so high, it tends to be the lightning rod for the city of Dubai. I've been there at times when there's been the weather coming through, and the top of the tower probably gets struck by lightning maybe every 5 minutes, because the building is grounded and the skin acts like a Faraday cage. There is no damage to the building. So after the building was completed and it was all washed, it was amazingly beautiful to see. So let's bring us to where we are today in the world, and we're very fortunate to be working in Sweden on what we call the Karla Tower, the Karla Tornet. In Gothenburg, it's a very, very, very sophisticated design using C70 cylinder strength concrete. It's a core and outrigger system, which is a very good system for a tall residential building. The foundations are quite an effort in themselves, because the soils near the surface are not so good for burying, but there's some good rock down deep which we have to get to. Here's some construction photographs of this very, very, very nice building in Gothenburg. But it's interesting to look at, where are we today in construction? Hopefully by now you see a slide of the construction in the last century up to the year 2000. And then I'm going to show you what it looked like after the year 2000. So as you compare the two, before 2000, after 2000, you can see that the project in Gothenburg is a part of a big worldwide boom in tall buildings. These are buildings that are over 200 meters tall, so the Gothenburg Tower certainly is part of this family. It used to be, you would say, if you were trying to do a tall building, it's structural steel. Now that is not true. If you look at the 100 tallest buildings by structural material, they are mostly either concrete or composite, a mixture of steel and concrete. Very few all steel buildings. And usually the concrete is very, very dominant in the lateral system because of its strength and stiffness. And sometimes some people ask, why do tall buildings? They're huge economic generators, and this is sometimes called the Burj effect. If you look at the Burj Khalifa, it makes a place. It plants the flag on the world stage, And every night of the year, thousands of people go to the Burj Khalifa to watch the light show and the fountain show and listen to the music and to see the building. It's quite remarkable. And after the design, some LED lights were attached to the mullions, so it has this incredible piece of creation of place. And the amount of jobs that this project has generated and the effect on the Dubai economy is incredible. And so with that, I want to finish with a photograph of the Burj Khalifa on the day it opened, when they had all these fireworks going off. This was in January the 4th, 2010. And I remember sitting there watching the fireworks going off and thinking, do we really want to do this? but it was well done. The building was not damaged by all the fireworks. And so with that, let me end my presentation, and I turn it back to you in Stockholm. Thank you.